Okay, so here's problem number one, or challenge number one. Challenge number one. Challenge is a better word than problem number one. Um, where did you steal my mouse? Where did my mouse go? I've never get myself to synchronize myself before I start. Adam, are you going to start reminding me to synchronize? And the gentleman sitting here, he always reminded me to synchronize one time. Okay, cool. Here's what we have, guys. We have very easy, very simple. A delta Y transformer with a primary 480 three-phase delta. The secondary is 4-wire Y solidly grounded. The size, the voltage, volt amp size of this transformer is 1,000 volt amp. The primary 480, the secondary 208, the impedance Z is the impedance. We call it the impedance. This is 1,000 kcm. 3 zeros in the front of it. Should be. Yeah, 1,000 kVA. I'm sorry, not kcm. 1,000 kVA. Yeah, we don't say volt amp, guys. We say kVA. 1,000 kVA. Yeah, it will be a million volt amp. Yeah, but we don't say when we size transformer, volt amp is small unit.
No,
for port.
you said the first time you said it was 1,000 volt.
1,000 volt. No, it's 1,000 kVA. I'm sorry, my apologies. 1,000 kVA. That's my cuff is not working this morning. 1,000 kVA. 281 23 phase 4 wire on the secondary, on the primary 480. What I would like you guys to do is find the following. Right, my email keeps popping up. Okay. I would like you guys to find the primary line current. The primary line current, we did it, guys. This is the current that's going right through here. Right through here. The secondary, then the primary coil current. The coil current is the current that's going through the winding. One more time. The line current is the current that's going through A, B, and C. The coil current is the current that's going through the windings. Okay, let's go ahead and start. When you find the line current, guys, it's called the LP. You take the kVA divided by 1.73, multiplied by the voltage, and here's your math. You take the 1,000 K divided by 1.73 times 480, and you get yourself a 1,204 amps, healthy amps. Here's your amps that you get for the line current. Very easy, very simple. Make sense? On the secondary side, on the coil current, the coil, guys, everybody can see where the coil current is going right in here? Oops, right here. The coil current is typically the phase current divided by 1.73. So it's a percentage of the phase current, not all of it. So you take your phase current, 1,204, divided by 1.73, and that you get yourself 696 amps. And that's my coil current. Now, who cares about the coil current? Typically, guys, coil current don't play a whole big of a role when it comes to sizing the fuses and circuit breakers. So, just as FYI only. For a transformer, it doesn't play a whole big of a role. So when you size your fuses and your circuit breakers and everything else, can you guys write yourself, put a star right here? This is the amp that you need to do. The line current is the amp that you need to do to size your fuses and circuit breakers and what's not. Any comments, any questions? Comments, questions? Let me know when I can go to the secondary. That's your primary side. Now my job, and your job, guys, is to size the fuses and the cables or the feeders on the primary and the secondary of this transformer. The fuses and the feeders on the primary and the secondary of the transformer. Cool? Okay. The secondary line current, guys, you take the kVA and you divide that kVA by the voltage of the secondary line to line. Very easy. Take the same kVA, divide it by 1.73 times the voltage is 208 this time. And if you guys do this, that'll give you a healthy 2777 amps. 2,777 amps. The secondary coil current, because it's a Y, can you guys see that? If it's a Y, in a Y, the line current and the coil current are the same. Can you guys see here's the coil current coming out and it goes all the way, the same current. Everybody can see that? The same current? Matt, especially Matt? Okay. So Matt, you're going to do some of these with us when you go to the motors too. So it'll be repeating yourself. Secondary coil current, it's the same one. It's 2777 volt amp. In a delta, guys, in a delta, the voltage stays the same for the coil and the line. In a Y, the current stays the same in a Y. The line current and the coil current stays the same. Okay, now I need to size my primary feeder. When you size your primary feeder, guys, sizing my primary feeder, I'll wait until you guys size my primary feeder. When you size the feeders and the fuses, you always use the line current. Did you guys hear me? The line current. Okay, so using the line current, we're going to come over here. We're going to assume it's continuous load multiplied by 1.25. So it's continuous load. Find the line current of this transformer. The line current of this transformer was 1204. That will get you a healthy 1505 amps. Okay, that's my amps. They don't make conductors that can carry this baby. So you take the 1505 amps divided by, did they do 7 here? Looks like 7 runs, divided by 7 runs, and that will give me 376 amps. Take this one, guys, to table 310.15B16 on the 75-degree column. And here's what you're going to get when you go there. You're going to get, I'm sorry, these are not.
95-degree column?
Yeah. No, 75. 75 degree, we don't use 90. This is 4, guys, I'm sorry, my apologies. Is it 4? Yeah. 4, I'm sorry. It looks, my 4 looks like 7s here. That's why I can't read my handwriting. So this is a 4, okay? 4, so that makes a lot of sense. This one, guys, you go to 7 and a 5-degree column, 75. When you go there, it will get you the following: 4 sets of what? 4 sets of 3 conductors, 500 kcm THHN. Any comments, guys? Any questions about that? Comments, questions? Now I sized my primary. What happened to the neutral? Do I have to size a neutral on the primary? Let's go look at it, huh? If you guys look at is there any neutral here? On the primary side? No. Why? It's a delta. Deltas don't have neutral. So I don't have to size neutral because it doesn't exist. Any comments, guys? Any questions? Comments, questions? So that's the feeder coming to the transformer. That's how much, 4 sets of 500 kcm, THHN. Assuming they're indoor. Why THHN? It's indoor. If it was THW, if it's outdoor, we'll use THHW. Good? Move yes, so. Okay. Now secondary feeder. Sizing your secondary feeder, guys. Same thing, you're going to take the 1.25, multiply that baby by 207.77. That will get you a healthy 3471 amp. Take the 3471 divided by 10. That will get you a healthy 347.1 amp. And this one, and this, take this one to 347.1 amp. Take it to table 310.15 B16, 75-degree column. That will get you 10 sets of 3 conductors, 500 kcm THHN. That's the size of your feeder. Okay. Do I have a neutral on the secondary? There was 4 wires, right? We have a neutral. So let's go size a neutral. These are just for the 3 phases. Why would I use always 500? Adam, you asked me which conductor should we size. When you size, guys, try to hover around 400. So if I give you 4,000 amps and you need to size them, try to divide the 4,000 by 400 or 350, something like this. That will give you 500 or 600 kcm conductor to pull. So when you size, when you start paralleling, if your conductor is larger than 400 amp, go around 400, 350, 400. Anything larger than 400, definitely start paralleling. Okay, for the neutral, guys, this is what we do for your neutral. My neutral, I'm going to take the 3471 amp that I got for the neutral, apply some derating on it. The first 200 amp, leave him alone. Anything larger than 200 amp, cut them by, anybody remember the magic number? 0.7 and add them up. So when you guys do the math, you're going to end up with 2,490 amp. Then you take the 2,490 amp divided by 10. You get yourself 249 amp. Why 10? Adam, because we parallel the phases 10 sets. Do I have choice when I parallel the phases 10? I have no choice. I have to parallel 10. So then you got yourself 249 amps. Take him to table 310.15 B16, 75-degree column. Gentlemen, you got yourself 10 sets. Here's my answer, 10 sets of 1 conductor, 250 kcm THHN. So that's the size of your neutral. Any comments, guys? Any questions? Karen, does it make sense what we did for the neutral? We just derated the neutral. Why would we derate the neutral this way? Because I have no idea what the neutral load is. Due to it? Okay. Why did I derate the neutral this way, guys? Because do you know what the neutral load on this transformer is? I have no idea. Right? I have no idea. So I assume that whole load here could be neutral, which is really very extreme assumption, and I cut it based on the code. 220.61 tells you to do so. Shall we go to number 7? Karen, we're good? Okay. Adam? Good. All right. The secondary, my friends, or number 7, oops. What I need to do here is I need to size my primary overcomputation devices. My primary overcomputation device, if you, Derek, if you go to 450.3b, you get the following. It tells you 2. Oops, we're going to use red here. 2.5. 2.5, multiply that baby by the primary current, which is 1204. That will get you a healthy 3010 amp. You take the 3010 amp, take it to 240.6, and if it's not a standard, lower it down, go down. Okay, you see that? To 300, 3000 amp. So your primary is going to be a 3000 amp. Your primary is going to be a 3000 amp. Does that make sense? Why did they go down? Because if you go to the table, it doesn't allow you to go up. If you can't go up and you can't stay where you are to find the fuse, you have to go down, right? So what we added, number 7, math, does it make sense? The primary, exactly the example that we did. Let's do the secondary, will ya? The secondary, guys, if you go to 450.3b, it will tell you it's actually 1.25. Multiply that baby by 277 and another 7. That will get you a healthy 3471 amp. You guys remember that? You take the 3471 amp, take that baby to table 240.6, and you got yourself a healthy 4000 amp fuse. You got yourself a healthy 4000 amp fuse. Piece of cake.
In terms of the secondary,
Yes. Now, why? If you look at the table, thank you for reminding me. When you look at the table, on the secondary, I always put these arrows, guys, that goes up and down. So you can go up. By the way, Derek, just because you're allowed to go up doesn't mean you go up. We're using the extreme here, guys, because we're in school. Typically, a lot of engineers will go down for design. Why do they go down? Safer. Did you guys hear me? We use software to size these, but your extreme situation, that's if you're going to go by the code, that's what the code says. You go up, you go up. So if you go to Mishad, Adam, and you see them going down, and say, Chad lost it, he told me to go up. Remember, up is a permission. It's up to you to take it. Does that make sense? You can go as low as you want on the circuit breaker, or as low as, typically if you're an engineer, a designer, you have to justify it though. Why did you go down? Because if it doesn't hold the load and keeps tripping, you have an explanation to do for the owner, right? Okay, grounding electrode conductor. Mr. Grounding electrode conductor, gentlemen, for this transformer. On the secondary side, we have 10 sets. You guys remember the 10 sets? Multiply them by the 500 kcm. The grounding electrode conductor always go by the secondary of the transformer, not the primary. That baby will get you 5,000 kcm. And then, if you take your 5000 kcm, take this baby to 250.66. We have been there many times, so if you guys take it to that baby, it will tell you all what you need is just one conductor, and it doesn't have to be more than 3-aught AWG, the one conductor number 3-aught. And let's use THHN. It's indoor, coming to the bottom, tied to the steel or the water in the building, to the steel, and it's a 3-aught. Any comments, guys? Any questions about the transformer problem? We have two more things to find out with transformer, then we're done with problem number one. Now, Matt, it is a crime against South Minneapolis. I want to pick on not to get this problem right. Okay? Straightforward. Guys, I know there's a lot of calculation that throw at you. So write yourself a cheat sheet, have it in front of you, where to go. I have a cheat sheet when I do my stuff. There's so much from now until you go with me. If you think you're gonna do what you did with Steve and have a couple of formulas and live with them, you're not gonna cut it. We do a lot of calculation, guys, much above and beyond what electrician can do. So to keep you sane, because you're engineers, you don't carry tools, right? Keep you sane, you have to write yourself a note. Later on, we're going to be sizing UPS and we're going to be sizing auto transfer switches and what's not. So to keep you sane, write yourself the notes. Otherwise, I mean, I don't know how I'd write myself notes. Does that make sense, Adam? The reason for in the electrical program, we go deeper into the sizing of a lot of equipments because eventually you're a journeyman, you're carrying tools, and unless you become a master, we push you a little bit harder. So people are going to pay you money because you do this stuff, not because you fix an outlet. Okay, main bonding jumper. The main bonding jumper for this transformer, guys, assuming it's utility transformer now, the same calculation. Here's your 250.28D1 based on NEC code 2010, 500 KCM, same calculation, 5000 KCM, and then there's a rule that says, guys, 00 KCM. Is this more than 1100 KCM? If the answer is yes, so if you go to this, it tells you, are you more than 1100 KCM copper? If your answer is yes, that will trigger another requirement that's called the 12.5% requirement. 12.5 times the 5000 K, and that will get you a healthy 625 KCM. There's one little problem. They don't make that size, right? They just don't make it. So what you're going to do then is you're going to take this one to 625 KCM, take it to chapter 9, table 8, and that will give you 700 KCM. A healthy 700 KCM. A healthy 700 KCM. Because they don't make 625. Right. Can you understand that when we size, ultimately we have to work with the equipment that manufactured, right? You can custom design yourself anything you want, but do you really want to pay for it? The last thing on this project is called number 11, guys. Short circuit. Short circuit. For the short circuit, guys, I short circuit always equal I secondary line over Z, the impedance. That's the formula for that, baby. This will equal, what's the primary voltage? The primary is, the secondary, 2777 divided by the impedance is 0.04. Now, Adam, the impedance is given in percentages. You write it in decimal. Yes, sir. Okay. I know, we didn't do it. I would like you guys to do it on this one. Absolutely. It's really nothing. The only new thing, you're absolutely right. We didn't do it on the first one. You know what? It's one formula. You take the line and just divide it by the impedance. You're absolutely right. We didn't do it on the first one formula. So if you do this, that will get you 69.4 kilo amp. So That's the 0.4 is given to you by your friend Chad. It's that 4% impedance.
Okay.
4% impedance. Z is the impedance of a transformer. What does it mean? What does it mean? Like Adam said, Chad, you didn't do it before because it's coming next project, Adam. Z guys will decide how much short circuit the impedance will allow to go through your building. Major thing. This is the available short circuit. Now, when I size my interrupting rating of fuse, it has to be able to handle 69.4 kiloamp or higher. So my next standard most likely will be 85,000 amp. If your fuse is incapable of handling the 69, it will explode. That's it. So that's a major part when you size your fuse. Now the fuse in the secondary, what was the size of the fuse in the secondary? 4,000, right? On the secondary, my fuse was 4,000. My fuse is going to be 4,000 foot load current and 85,000 interrupting rating. Why 80,000? Because the next standard 69.4, I believe. After that, they go to 85. There's 65 and 85,000. How do I know that? That's with Cutler Hammer Square D guys literature. They tell you. Okay. Do you need to know it for the test? No. All what you need to know for the test is this value. Any comments, Adam? Make sense? Okay. All right, so let's go to problem number 2. And that's about it. Problem number 2 is a load calculation. Commercial building office style load calculation. It's a 3, you guys have it, right? You have this information. I copied this for you. Everybody knows. The sheet that I gave you guys have this info. I have a commercial building, office type. The voltage is 482.77. I'm going to feed it. It's a 3-phase. This office has the following. It has an AC unit, 15 horsepower, 3-phase. It has an electric heat of 150 kVA. The area of this building is 50,000 square foot. It has one sign, it has 200 track lights, 50 multi-outlet assembly, 250 receptacles because Karen decided to, she likes receptacle through 250 in them. Computer load, now this is a new, Adam, I don't think we did. Computer load, this is, assume it's standalone computer load of 20 at 20. I have computer load 20 amps at 120, 10 circuits. 10 circuits, did you guys hear me? 10 circuits, each one of these circuits is a 20 amp. It's dedicated for data in a computer. And I need to size, what do I need to do? Size the service. Just one panel. You guys have done it with me, size 3 panels. We're going to do one panel, the main panel. Any question, guys, about what we're trying to achieve? Any question about what we're trying to achieve? Is it achievable? Shall we go? Okay, let's go ahead and do it. The first thing, how do you eat a chicken? One bite at a time. Elephant is too big to eat these days. We're going to lower it down to a chicken, right? How do you eat an elephant? One bite at a time. These are the steps that you guys did with Chad for the load count. We went over them, so we'll test you one more time over there. Okay, general lighting, 220.12. So first of all, you have to go and find yourself the general lighting. And based on the general lighting for this building, you take the 50,000 square foot, multiply that baby from this table by 3.5, multiply it by 1.25 because it's continuous load, and you just got yourself 219 kVA. So you take the 50, multiply by 3.5 times 1.25, get you 219 kVA, and that will be the size of your general light from the code. Track lights. Do I have now? Here's my question for you. Do I have an actual light to compare with? They didn't give me an actual light, did they? I don't have an actual light. I have track lights. That's just a specific light. I don't have general light. So do I need to compare this with anything, Derek? No. Why? If I told you there are also, this is how I can say, there's also 250 kVA worth of lighting fixture there. 250. Which one would you use? The largest, the 250. In this case, they are not telling you, they haven't designed the lighting for the building. So what do? You assume it's going to be that much, the worst case scenario. Track lights. For your track lights, my friend, it's piece of cake. You take the code says every 200 kVA, give you every 2 feet, give them 150, every 2 feet, give it 150 volt amp. Since it's continuous load, don't forget to multiply it by 1.25, and that will get you a healthy 19 kVA. Why? These are volt amps. This is volt amp. These are feet. These are feet. You can see what it is? 200 feet divided by 2, because for every 2 feet, you give it 150 volt amp. Your sign is very easy. You assume a 1200 volt amp for your sign, multiply it by 1.25, and that will get you 1.5 kVA. Can I emphasize, guys, Matt, that like here, I already divided by 1,000, right? Everybody understand? I'm not sure I'm divided by 1,000. You guys are big boys and girls now. We don't divide by 1,000. A K, we know how to find a K, right? Everybody understand? When you guys are doing your math, if you do this strictly, you say, Chad, where's the 1,000, right? I didn't do the 1,000. You know that this is 1,500 volt amp is actually a 1.5 kVA. It's not worth writing. Should we go to the heat? Cool. Okay. The next step, my friend, is heat and air conditioning. So for my heat, guys, is given as 150 kVA. My heat is 150 kVA. Air conditioning, though, my air conditioning, I need to do calculation for it. I have a 15 horsepower. Take that baby to table 430.15 B16. No, Chad, you're wrong. This is going to be going to table 430.250. 250. That will give you guys the full load amp is 21.8 amps under 480 volt. That will get you 21.8 amps. Cool. Then here's what you need to do. You have to then you take, put this one here. Then you take 1.73, multiply it by 480, multiply it by, I don't want to use this, let me see here. Do it, how am I going to do it? 1.73 times 480 times the current that we came up with, guys, is a 21 point, why did I say 0.8? I'm sorry, this should be, I think I'm reading it, this just should be 21. Can you guys change this one to 21? 21, please. So I think I read the definition. So there will be 21. That's my amp. Cool. And then you have to increase the amp by 1.25. Do you guys remember why? Why do we increase? Because it's only one of them. 1.25. Okay. And that will get you the following. That will get you, there you go. A 21.8 kVA. That's where the 21.8 kVA came to be. That's the first motor. And I don't know if I mentioned, if you guys go up back here, AC units, I don't think I said here. Oh boy. 15. Oh, I forgot to mention there's 15 of them. Can you guys see that? Everybody saw that? There's 15 15 horsepower. I should change the number from 15. There's 15 AC units. Each one of them is 15 horsepower. Can I have thumbs up, Chad? We got that one? Because that's going to confuse you a little bit. There's 15 of them. Okay. The first one you multiply it by 1.25, and here's what it shows. So that would be the first one. The second calculation that you need to do here, guys, is you do the same thing. Then you're going to take the 14 of them, the leftover, multiply it by 1.73 times 480 times the amp is 21. So you take the largest motor, add 25% of it, the leftover, leave him as is, and we'll get you 244 kVA. Gentlemen and ladies, then you add these two together, and the step that you add these two together, and you're going to end up with, when you add these, you're going to end up with what? You're going to end up with 5.8 kVA. That's your ultimate value that you're going to be using. Then you're going to choose the largest of heating and cooling. And the largest of heating and cooling, gentlemen and lady, is 265.8. That's your largest value that you're going to be using. Actually, I shouldn't have write this one here. There you go. That's the largest of the two that you're going to be using for your calculation. Did we do any mistakes in the math? One more time. We take the first motor, guys, increase it 25%. All the other motors, leave them as is. Add them up. Don't forget to, how am I going to emphasize that one? Maybe put this here, add them up. So add them up. You get your 265.8 kVA. That's your load for the AC units. And choose the largest. So, and I'm very clear, 265.8 kVA is more than 150 kVA. So you choose the largest. Any comments, guys? Any questions? Make sense? Yes? No? Derek? We're good? Doing calc? Matt? Okay. Let's go to the computer load. This is a new load. I can't recall if I did that one for you. For my computer load, guys, is my computer load. I will remind you, it's a 20 amp circuit multiplied by 120 volt, multiplied by 10 of them. 10 is their number, and we're gonna get you a 24 kVA. 24 kVA. That's dedicated to computer load. Now you could increase it by 25%, but we're not going to do it. That's load, just as is. There's 20 circuits dedicated to laptops. We're not going to derate them. These are non-deratable. Then you go to your receptacle. The receptacle load, guys, we have 250 receptacles at 180 for a total load 45 kVA. We do have also a multi-outlet assembly. Multi-outlet assembly, it's 50 of them, non-simultaneous. 50 feet of multi-outlet assembly. For every 5 feet, you give it 180 volt amp. That will get you 1.8 kVA. When you add these two together, you get 6.8 kVA. Now, is this simultaneous or non-simultaneous? These are non-simultaneous. Why? Did I say anything about simultaneous for multi-out assembly? So you divide it by 5. That 5 comes for every 5 feet, there is 180 volt down. Then you take the demand, guys, which is 46.8K. Take this one to table 220.44. This is how you derive it. The first thing, K, leave him alone. Anything higher than 10K, which is 46.8K, minus 10K. This number, you multiply it by 0.5, and then you add them up. You add them up, they'll give you 29 kVA. 29 kVA. Apply the demand for them. Any comments, guys? Any questions? Comments, questions? So that's how you demand them. Any comments, any questions? Cool. Okay, now we need to compare the receptacles, guys, with the building, what the building give you. So receptacles based on 220.14, the building, 50K square foot multiplied by 1, that will give you 50 kVA. Then you're going to choose largest of G1 and G2, the 2 steps. Remember that 2 is the largest. So very clear, the largest is 50 kVA. That's the number that you're going to use to carry downstream. Why? Because if you guys go back, I have 29 kVA demand and 50 kVA demand. Which one are you going to use? The largest. 50 kVA. We're done with the load calc. Let's go size the equipment now. You're done with the load calc. Next, we will size the equipment. Everybody's good? Can I move? Yes, no? Okay, thank you. Now next, guys, building demand load. Building demand load, you're going to add all these steps that we just went through. You guys, all these steps. So you're going to add the general lighting load, the track light, the sign. You're going to add the heating and the cooling, the largest of the heating and the cooling. You're going to add the computer load. You're going to add the receptacle demand, that step here. When you add them all up, here's what you're going to come up with. You're going to add the following. You're going to add 21.9, that was, I believe, for the light. 19, can't recall what that was for track lights, I think. 1.5, that was for the sign. I'm adding, not multiplying, Chad. Have I lost that? I'm adding them. So we'll 219 plus 1 plus 19 plus 1.5 plus 265.8, that's for the HVAC, plus 50, that's for the receptacle. If you add, okay, we forgot 24. What was for 24? Plus 24 plus 50. Did I forget any? The demand, we already demanded it. That one, that step. That one, 29. You compare it with the 50, and you choose the largest. You're absolutely right. You compare with the 50 and choose the largest. That's all what we have. So then your total is 5 79.3 kVNA. After that, it's piece of cake, guys. Your demand, that's your demand kVA. Demand current for the building, you take this number that you just came up with, divided by 1.73 times 480, because that's the voltage system that you're feeding your building. You end up with 698 amps. 698 amps. Then you take the 698 amps, take it to 240.6. And you go up to the next standard overconduction device to find it. That will give you a healthy 700 amp 3-pole circuit breaker. You guys see that? So my panel, the overconduction device and the panel will be sized to 700 amp. That's my overconduction device. That's my overconduction device. Did you guys get DeWalt? Okay, so you need to get DeWalt tomorrow to get some number. One number from it. So that's the overconduction device. Let me know when I can move. Good. You guys are faster than me. Not hard to be, huh? Panel size. The panel, everybody knows the difference between the overconduction device and the panel. The overconduction device can be lower than what the panel is rated for. So the panel size, you take the 698 amps, take them to DeWalt, page 3-13. That will get you an 800 amp panel. This is the guts, the copper inside the panel. The last thing guys going to do is feeder size. I say match overconduction device. For feeder size, I say match over current protection device. Okay, my overconduction device is 700 amp. I want to parallel. I divided by 2 so I can parallel. I came up with 350 amp. You take this one to healthy 310 table, 310.15 P16, 75-degree column always, and you do 2 sets of 3 conductors, 500 kcm THHW, most likely. And that's the size of the phases. That's the phases size. Does that make sense? 3 conductors for the 3 phase. Now we're going to go find the neutral when you guys are done. Right? The neutral will be different. We'll go size the neutral. So when you guys are done, what I'm going to do, I'm going to go back into these loads and just highlight what counts for the neutral and what's not. Come back here, add them up. It takes me a second, literally. And then size the neutral. But I need to go back and see what counts for a neutral load and what's not. And the tricky one, Adam, anything that connected line to neutral, count as a neutral load. Anything 3-phase, open that window, throw it outside. Does not contribute to the neutral. Okay, so let's go back, guys, and look at all these loads that we did. And I'm going to put next to them N for neutral in green. So can you guys go to the general light? The first one that we did, general light. Can you do me a favor? Right next to this number, put N. What does N mean here? N count as a neutral. Let's go to the track light. Right next to the track light, put N. Also, N counts as a neutral. The sign, N. How do I know? All your lights, guys, will be burning at 277. Right? If there's any light that burning, almost all your lights are running typically 277 or 120. Your sign will be running at 120 or 277, so it will contribute to the neutral, assuming this is a 277 light. So these all will count. Let's go to the heating. Gentlemen, the heating, where's my heating and cooling? Would this count as a neutral? The heating and cooling, the demand, right here, where the demand is. Does this count as a neutral? Remember, these are 3-phase. These are 3-phase equipment. I don't want to write it in neutral. This is everything here is three-phase. So what I'm going to do right here, just put an X, green X, would not count as a neutral. As a neutral would not count. Okay, keep moving. Let's go to the computer load. The computer load is N, will count as a neutral as is. The receptacle load atom, they will, except which number? Not these numbers, all the way to this number. That's the number that we carry because that's the demand for all the receptacle. Ladies and gentlemen, that's all the loads that's going to count. Do I need to do any calculation? Just go put N next to them. Okay, so now we're going to go at them. Only the ones I put N next to them. So let's come over here. So I have the first thing I'm going to do, design, okay, the neutral. I have 219 plus, that's a light, plus 19, the track light, 1.5, the sign, plus 50, plus 24, let's do 24, the computer, 24, plus 50, equal, so we got that one, plus 50 equal, we have 313.5 kVA. That's what I come up with. Okay? 313.5 kVA. Now we need the current, piece of cake. You take this number, 313.3 K, divided by 1.73 times the 480, and that total will equal 377.5 amp. 377.5 amp. That's the amp for your neutral. You can see what the amp for the phase was, 698. The amp for the neutral, almost half of it. Very typical on panels like this. The amp will be a half, typically a half to 2/3. Okay, so now we have our amp. Shall we go size the amp? When you guys are ready? Wow. You ready? Cool. Now we're going to go to size the amps. So I'm going to take this value, guys, which is 377.5 amps. Take it, first we're going to take it to 220.61B. The first 200 amp, leave them alone. Anything higher than 200 amp, cut them by 0.5. That's always the neutral. Then add everything up. That will give you another reduction, 324 amps. So now you reduce, guys, you demand the neutral one more, right? Can you see that? You cut the neutral one more. And finally, gentlemen, ladies and gentlemen, you take your 324 amps. Now, I'm sure Terry say, Chad, I can carry this with one conductor. But remember, Adam, we parallel the phases, we have to parallel the neutral. You have no choice. You parallel phases, you parallel neutral. So I parallel two sets, I have to parallel two sets, regardless. I came up with 162 amps. Take this one to, and 2 amps. Take this one to table 310.15 B16, 75-degree column. That will give you two sets of how many conductor? One conductor, number 2 at AWGTHHN.
That one you're at 0.5 and you mean 0.7
Which one?
on the top right corner for the 377.5.
377.
0.7 is the derating factor.
This derating factor is, I'm sorry, 0.7. You're absolutely right. I think I'm still in the. Can you guys change that one? Thank you. This one should be 0.7. Thanks. My derating factor is 0.7. Otherwise, math wouldn't do it. Wouldn't cut it. 0.7. Okay, now we size the neutral. We have two sets of neutral. We bring a conduit, guys, put 4 conductors in it. What was the size of the phases? The size of the phases were 500. So 3 conductors, 500, and 1 conductor, 2 on. Grounding electrode conductor and main bonding jumper, and then we're done, gentlemen. Grounding electrode conductor. Here's what you do. You take the 2 for 2 sets, multiply them by 500 kcm. That'll get you a healthy 1000 kcm. And then you take 1000 kcm, take it to table 250.66, and that'll get you a healthy 1 conductor number 2 aught AWG THHN. THHN. Does that make sense? Why did I multiply by 2? Because I parallel 2, right? If I parallel 3, what do? Multiply by 3. The last one, gentlemen. The last one. Good? You guys are always ahead of me, man. I finish and you're done. Okay. Let me know when you're good. Good, good. Adam, we're good? Okay, thank you. The last one is main bonding jumper. Main bonding jumper or system bonding jumper, depending on the transformer used. Same calculation, guys. You take the 2, multiply it by 500 kcm, get you 1000 kcm. Then you ask yourself, kcm, is 1000 kcm more than 1100 kcm? The answer obviously is no. Did you guys hear me? The answer is no. Then do I have to trigger the 12.5% multiplier? No. Since the answer is no, then you take 1,00 kcm, take this baby to table 250.66 directly, and that'll get you a healthy 1 conductor 2 aught AWG. Gentlemen, you know how to do this? You got your A. And lady. So we have a quick break, and then I need another maybe 10 minutes for the theory, and then we'll do some Revit. Thank you.